Humanity's journey is a chronicle of ambition, fueled by an insatiable desire to understand, build, and transcend limits. From the earliest tools to the most complex machines, our path has been illuminated by the audacious visions of engineers. These are the blueprints of tomorrow, designs that, at their inception, often seemed impossible, yet ultimately reshaped our very existence. This film explores how these groundbreaking engineering concepts, from the Renaissance genius of Leonardo da Vinci to the modern marvels of SpaceX, have not merely advanced technology, but fundamentally altered the destiny of humanity. Our journey begins in the vibrant intellectual ferment of the Renaissance, a period defined by a fervent rediscovery of knowledge and an explosion of artistic and scientific inquiry. In this era, one figure stands as an unparalleled embodiment of human potential: Leonardo da Vinci. Born in 15th century Italy, da Vinci was not merely a painter, he was a polymath whose curiosity extended to anatomy, botany, geology, and, critically for our narrative, engineering. His notebooks, filled with intricate sketches and observations, offer a window into a mind centuries ahead of its time. Among da Vinci's most profound legacies are his personal notebooks. The Codex Atlanticus, for example, a vast collection of his writings and drawings, documents thousands of his inventions, observations, and theoretical designs. These aren't just artistic doodles, they are detailed engineering studies, complete with explanatory notes and often multiple perspectives of the same mechanism. According to art historians and engineers who have meticulously studied these manuscripts, they reveal a rigorous, empirical approach to problem solving, underpinned by a profound understanding of natural principles. Perhaps da Vinci's most iconic engineering visions relate to flight. Centuries before humans would take to the skies, he conceived of numerous flying machines. His designs included the aerial screw, often considered a prototype for the modern helicopter, featuring a helical rotor designed to compress air. He also meticulously sketched ornithopters, machines with flapping wings, inspired by his extensive studies of bird anatomy and aerodynamics. These radical concepts, documented in his notebooks, demonstrate an early understanding of principles critical for sustained flight. While da Vinci's designs were breathtakingly ambitious, many remained unrealized during his lifetime. Historians of technology suggest that this was largely due to the practical limitations of 15th and 16th century materials and manufacturing capabilities. The lightweight, strong alloys and powerful engines necessary for flight or complex hydraulic systems simply did not exist. His deep understanding of theoretical mechanics often outstripped the available means of practical implementation, making his blueprints more prophecies than immediate prototypes. Despite their initial unrealized state, Leonardo da Vinci's visionary approach profoundly influenced engineers centuries later. His systematic method of observation, analysis, and detailed conceptualization laid foundational groundwork. Scholars such as Dr. Michael White, author of Leonardo, the First Scientist, argue that da Vinci's work established a precedent for empirical engineering, demonstrating how detailed conceptual design could precede technological capability. His blueprints, though dormant for centuries, proved that human ingenuity could conceive of futures far beyond the present. For centuries, humanity's engineering progress unfolded gradually, often relying on incremental improvements to existing technologies. Yet, the seeds sown by visionaries like da Vinci began to germinate as new scientific understanding and material sciences emerged. The transition from individual genius to collective industrial effort marked a pivotal shift. This era, characterized by groundbreaking inventions and the harnessing of new forms of energy, would dramatically accelerate the pace at which humanity could transform its environment, setting the stage for truly global change. The late 18th century witnessed an invention that would fundamentally reshape human destiny: the improved steam engine. Developed by Scottish engineer James Watt, this machine dramatically increased efficiency and reliability compared to earlier designs. Watt's innovations in steam power, according to industrial historians like Dr. Peter R.M. Mathias, were not merely technological advancements, they were the catalysts that ignited the Industrial Revolution, enabling unprecedented levels of power generation and mechanical work. The impact of Watt's steam engine rippled across society, altering virtually every aspect of human life. It powered factories, enabling mass production of goods on an unimaginable scale. It revolutionized transportation, driving the first railways and steamships, connecting distant lands and facilitating global trade. This era, characterized by the widespread application of engineering, demonstrated the profound power of applied science and technological innovation to transform economies, demographics, and the very fabric of society, establishing new blueprints for progress. While Leonardo da Vinci conceived of flying machines, it took centuries for the dream of human flight to materialize. The path was paved by numerous experimentalists and theorists, including Otto Lilienthal, whose glider flights in the late 19th century provided crucial data on aerodynamics. These early pioneers, building on centuries of scientific inquiry and practical experimentation, relentlessly pursued the challenge of controlled flight, facing skepticism and repeated failures but fueled by an unwavering vision of a skyfaring humanity. The culmination of these efforts arrived on December 17, 1903, in Kitty Hawk, North Carolina. On that day, Orville and Wilbur Wright achieved the first controlled, sustained flight of a powered, heavier-than-air aircraft. This monumental feat, documented by contemporary reports and photographs, was not a sudden breakthrough but the result of years of meticulous research, design, and iterative testing. The Wright brothers' flyer represented a practical blueprint for aviation, moving the concept from theoretical sketches to tangible reality. The success at Kitty Hawk sparked the age of flight. Within decades, aviation evolved from a dangerous novelty to a transformative force. Airplanes became instrumental in military strategy during world wars, and soon, commercial airlines began to shrink the world, making international travel accessible. The ability to traverse vast distances rapidly fundamentally altered geopolitics, trade, and cultural exchange. According to aviation historians, the Wright brothers' ingenuity literally opened up a new dimension for human activity and expansion. As the 20th century progressed, humanity's gaze began to turn upwards, beyond the atmosphere. The ambition to reach space, once the domain of science fiction writers like Jules Verne, started to take concrete form in the minds of engineers. The development of rocketry, initially driven by military applications, soon presented the possibility of venturing into the cosmos. This new frontier, with its seemingly insurmountable challenges, would demand an unprecedented scale of engineering vision, collective effort, and national dedication. The space race, a defining characteristic of the mid-20th century, emerged directly from the geopolitical tensions of the Cold War. The United States and the Soviet Union, locked in an ideological struggle, viewed achievements in space as potent symbols of technological superiority and national prestige. This rivalry, while born of conflict, inadvertently propelled humanity's engineering capabilities forward at an astonishing pace. The push for dominance became a powerful, albeit unintended, catalyst for some of our greatest scientific and technological leaps. The world watched in awe and, for many in the West, with alarm on October 4, 1957, when the Soviet Union launched Sputnik 1. This small, spherical satellite became the first artificial object to orbit Earth. Sputnik's simple beep-beep signal, broadcast from space, sent shockwaves across the United States. According to contemporary news reports and historical analyses, it was a profound psychological blow, demonstrating Soviet technological prowess and initiating a frantic acceleration of the American space program. 4 years later, on April 12, 1961, the Soviet Union again stunned the world by sending the first human into space. Cosmonaut Yuri Gagarin orbited Earth aboard Vostok 1, completing one full revolution in 108 minutes. Gagarin's mission cemented the USSR's lead in the early space race and offered humanity its first direct glimpse of Earth from the cosmic perspective. His flight, meticulously planned and executed by Soviet engineers, proved that humans could survive and function beyond our planet's protective atmosphere. The Soviet successes galvanized the United States. On May 25, 1961, President John F. Kennedy issued a daring challenge to the nation to land a man on the moon and return him safely to Earth before the end of the decade. This ambitious blueprint, seemingly impossible at the time, required unprecedented dedication and innovation. Kennedy's declaration, widely reported and later analyzed by historians like Robert Dallek, galvanized public support and immense federal funding for the Apollo program, transforming the space race into a lunar marathon. The Apollo program, a monumental engineering undertaking, involved hundreds of thousands of individuals and countless subcontractors. The ultimate blueprint was the Apollo 11 mission. This complex system, from the Saturn V rocket to the lunar module, required the invention of entirely new materials, guidance systems, and life support technologies. Every component, every calculation, every procedure had to be executed with near-perfect precision, pushing the boundaries of what was technologically feasible for human spaceflight. On July 20, 1969, the world collectively held its breath as Apollo 11's lunar module, Eagle, touched down on the Moon's Sea of Tranquility. Hours later, Neil Armstrong stepped onto the lunar surface, uttering the immortal words, "That's one small step for man, one giant leap for mankind." This moment, broadcast globally, was not just an American triumph, it was a testament to humanity's collective will and engineering prowess. It fundamentally shifted our understanding of our place in the universe. The Apollo program's impact extended far beyond a flag on the moon. The immense government investment spurred rapid technological development across various sectors, including computing, materials science, and rocketry. According to economists who studied the program, the spin-off technologies benefited numerous industries, from medical imaging to satellite communication. Apollo's success reinforced the idea that with sufficient vision, resources, and engineering dedication, humanity could achieve the seemingly impossible, charting new blueprints for collective action. Beyond the technological achievements, the space race profoundly shifted human perspective. Images of Earth, a fragile blue marble suspended in the vast blackness of space, introduced what astronauts later termed the overview effect. This new vantage point fostered a heightened sense of global unity and environmental awareness. For the first time, humanity saw itself not as divided nations, but as a single civilization inhabiting a shared home, a profound shift attributed to the engineering visions that enabled space travel. Following the initial intensity of the space race, particularly after the Apollo missions, the pace of human deep space exploration seemed to decelerate. Government-funded programs focused on Earth orbit with projects like the Space Shuttle and the International Space Station. While crucial for scientific research and international cooperation, the grander visions of lunar bases or Mars colonies appeared to recede into the distant future. The challenge for new engineering blueprints became not just reach, but sustainability and cost-effectiveness. As the 21st century dawned, a new paradigm began to emerge in space exploration: private enterprise. Driven by individuals and companies with audacious long-term visions, this shift sought to revolutionize access to space, making it more affordable and accessible. This approach contrasted sharply with the Cold War's government-led, often budget-intensive, programs. The new blueprints were not just about reaching space, but about democratizing it, fundamentally altering the economics and scalability of space operations. At the forefront of this commercial space revolution stands SpaceX, founded in 2002 by Elon Musk. Musk's stated goal was profoundly ambitious: to reduce space transport costs and ultimately enable the colonization of Mars. According to early interviews and company statements, this vision was born from a concern for humanity's long-term survival and a belief that becoming a multiplanetary species was essential. This wasn't merely about launching rockets, it was about laying the groundwork for a new chapter in human destiny. A cornerstone of SpaceX's strategy to reduce costs and achieve its long-term goals was the development of reusable rocket technology. The Falcon 9 first stage, designed to land vertically back on Earth or on a drone ship at sea, represented a monumental engineering breakthrough. Before this, rockets were largely expendable. As aerospace engineers have noted, this reusability dramatically cuts the cost of access to space, transforming rockets from single-use vehicles into something more akin to aircraft, ready for multiple missions. The successful implementation of reusable rocket technology by SpaceX had immediate and profound implications. By making launches significantly cheaper, it opened up space to more players, from smaller satellite companies to scientific research institutions. This innovation directly supports Musk's vision of expanding humanity's presence in space. Analysts at institutions like the Space Foundation recognize this as a critical turning point, shifting the economic blueprint of spaceflight from prohibitively expensive to increasingly sustainable and scalable. Beyond launching satellites, SpaceX also developed the Dragon capsule, capable of carrying both cargo and, eventually, crew to the International Space Station. The first private company to successfully dock with the ISS, SpaceX quickly became a vital link for NASA. This demonstrated the reliability and safety of commercial spaceflight, further solidifying the role of private enterprise in human space exploration and proving that their engineering blueprints could meet the rigorous demands of human spaceflight. SpaceX's most ambitious blueprint to date is the Starship project. Designed as a fully reusable, interplanetary transport system, Starship aims to carry hundreds of people and vast amounts of cargo to the Moon and Mars. With its colossal size and advanced propulsion, it represents an engineering vision on a scale not seen since the Saturn V rocket. Its development, characterized by rapid prototyping and iterative testing in Boca Chica, Texas, embodies a new approach to complex aerospace engineering. The ultimate goal for Starship, as articulated by Elon Musk, is to make humanity a multiplanetary species by enabling the establishment of a self-sustaining city on Mars. This vision, far more ambitious than mere exploration, requires not just powerful rockets but an entire ecosystem of supporting technologies. Starship's engineering blueprint, if successful, would not only reshape space travel but fundamentally alter the trajectory of human civilization, offering an escape from Earth-bound limitations and vulnerabilities. The trajectory from Leonardo da Vinci's aerial screw to Elon Musk's Starship reveals a striking parallel in visionary engineering. Both men conceived of radical machines far ahead of their time, driven by a profound belief in human potential. Da Vinci's concepts, though constrained by Renaissance technology, laid intellectual groundwork. Musk's projects, while leveraging modern advancements, similarly challenge established norms and push the boundaries of what is considered achievable, offering bold new blueprints for humanity's future trajectory. From the steam engine's capacity to power an industrial age, to the Wright brothers' flight that shrank our world, and the Apollo program's achievement that allowed us to gaze back at our planet from afar, engineering visions have consistently redefined human destiny. Each leap, driven by audacious blueprints, has expanded our physical and intellectual horizons, transforming how we live, work, and perceive our place in the cosmos. These aren't just technical achievements, they are cultural and existential milestones. The journey from Da Vinci's unbuilt machines to SpaceX's reusable rockets underscores a fundamental truth about human ingenuity: it is a relentless, iterative process. Failures are met with new designs, limitations with innovative solutions. Every successful blueprint builds upon the knowledge and ambition of those that came before. This continuous pursuit of what lies beyond the known is the engine of progress, ensuring that humanity's story will always be one of discovery and ambitious engineering. While engineering visions have propelled humanity forward, they also present new challenges. The scale of future endeavors, particularly in space, demands sustainable practices and ethical considerations. As we plan for multiplanetary existence or exploit extraterrestrial resources, the blueprints must increasingly incorporate environmental stewardship and long-term viability. The destiny of humanity, shaped by our engineering, will depend on our ability to not only innovate but to do so responsibly and thoughtfully. The story of engineering vision shaping human destiny is not a closed chapter, it is an ongoing saga. Each generation faces its own unique challenges and opportunities, demanding new blueprints for a better future. Whether in energy, healthcare, artificial intelligence, or deep space exploration, the spirit of innovation, the courage to dream big, and the meticulous work of engineering continue to be the driving forces. The next set of world-changing blueprints awaits the minds brave enough to conceive them. From the parchment of a Renaissance master's notebook to the launch pads of a private space company, the evolution of engineering visions tells a powerful story. It's a testament to the enduring human spirit that seeks to build, to explore, and to transcend. These blueprints, whether realized in their own time or centuries later, have not merely defined eras, they have fundamentally directed the course of human civilization, proving that the greatest machines are born from the greatest dreams, forever shaping our destiny.